we have two goals in this video. First, we want to find a simple way of dealing with multiple inputs. When a function takes 2, 3 or more inputs, we want to be able to handle them all in a systematic way. This will make functions easier to construct and to work with. The second goal is to understand how these multi-input functions behave when we change to a different basis. We want those changes to be predictable, so that we know how to correctly adapt the coordinates and coefficients in our mathematical expressions. And specifically, we want to figure out how to construct mathematical values that don't depend on our choice of basis. Tensors allow us to meet both of these goals. And along the way, they will also force us to rethink the difference between active functions and passive data. So we have a lot of discoveries waiting for us. Let's do this. We start from single input functions and then we combine them into functions that take more inputs. These bigger functions are called tensors. We laid out a detailed example in the previous video, so take some time to watch it first. We want our tensors to take a given number of vectors and/or dual vectors as inputs. When a tensor takes p vectors and q dual vectors, we say that it has a rank of p, q. The output of one of our functions should always be a real number. We also want our functions to be linear, which means that if you replace one of the inputs by a linear combination, the new output will be the same linear combination of the separate outputs. Those are the requirements we have for tensors. You already know the single input pieces from which we will build bigger tensors. There are two kinds, one-forms and vectors. A one-form is a linear function that takes a single input vector. So, according to our naming convention, it's a tensor of rank 1, 0. It produces a real number, so it meets all the requirements. We already saw that, just like any kind of functions, one-forms can be scaled and added, so you can treat them as vectors. We call them dual vectors or covectors, to distinguish them from traditional vectors. Notice what just happened here. You typically think of a function as something active, something that chops and mixes and transforms its inputs into outputs. But now we are suddenly treating them as vectors, which we typically think of as passive objects that just sit there, waiting to be operated upon. Vectors don't actively do anything. They're just lists of numbers. Well, the thing is that in tensor algebra, this distinction between active and passive, between transformations and objects, between functions and data, becomes fluid. Instead of a distinction, we will come to think of it as just two different perspectives on the same thing. We can practice this new perspective on the second kind of elementary piece. A traditional vector can be treated as a linear function that takes a single one-form and turns it into a real number. So vectors would be tensors of rank 0, 1. Once again, we can look at a vector as a passive object or an active function, depending on the context. Last time we looked at linear transformations or matrices. I showed you that a matrix is a combination of a vector and a dual vector, glued together by the tensor product. The vector has rank 0, 1, and the dual vector has rank 1, 0. The bigger tensor, the matrix, has a rank of 1, 1, because it takes a vector and a dual vector as input. The word linear transformation betrays an active perspective. It's a function. It transforms one vector into another. But you can easily treat matrices like objects. I mean, they are just tables of numbers, or tensors that we create by sticking two pieces together. And just like those pieces, matrices can also be scaled and added, so they are yet another kind of vectors, if you will. So you see that the distinction between linear functions and vectors is merely a matter of taste. Let's get a bit more creative and glue two dual vectors together. The resulting tensor is a function that takes two vectors as input, so it has a rank of 2, 0. In more traditional linear algebra, this is known as a bilinear form. As always, the word form means that it returns a real number. And bilinear means that it takes two input vectors and treats them both linearly. But again, we can also treat these tensors as objects that we can manipulate. We can keep going like this. You can construct a 2, 3 tensor by tensoring two dual vectors together with three vectors. Remember that the tensor product simply brings these parts together, but prevents them from touching each other. Instead of annihilating in vector-covector pairs, they just patiently wait their turns for external inputs to arrive. If the input is a vector, we pass it to one of our internal dual vectors, and together they produce a real number. If the input is a dual vector, we pass it to an internal vector, and out pops another real number. At the end, all those real numbers just get multiplied into the final result. You can tensor any two given tensors together into a bigger one. The end result is just a bigger bunch of parts all glued to each other. The ranks simply add up, and the result is both an object that can be added and scaled, and a linear function with multiple inputs. These tensors help us accomplish our first goal. They make multilinear functions much easier to work with. They give us a choice. You can take your inputs one at a time, or all at once. When a PQ tensor takes only a single input, the input gets introduced to one of the internal parts. They get together, and they give birth to a real number. The total number of internal parts then decreases by 1, so you are left with either a p-1, q tensor, if your input was a vector, or p, q-1, if it was a dual vector. It's actually very simple. When you take your inputs one at a time, you keep lowering your rank step by step until only a real number remains in the end. And a real number is just a 0, 0 tensor. This is all very nice and predictable, but it gets even better. We can also tensor all of our inputs together into a single big object. We can then pass that object in a single blow as input to the other tensor. All of the parts of the input annihilate with all of the parts of the tensor to produce the final real output all at once. I hope you see how we are mixing our two perspectives here. The thing at the bottom acts as a function, and the thing at the top acts as its input, a passive object. But they are both just tensors, so you could also think of it the other way around if you like. Or, as before, you could say that they are both passive, and it's the inner product between them that actively compacts them into a real number. This fluid, flexible duality between objects and actions makes tensors very useful. Anyway, we should break out the cake and apple juice, because we have just achieved one of our goals. We have turned a multi-input function into a single input function. We basically do this by gluing all of the inputs together so that we can pass them around all at once. This is one of the main purposes of the tensor product. Mission accomplished. Vectors are geometric objects. It's only when you decompose them in a specific basis that they become lists of coordinates. When you change to a new basis, the coordinates will change too, and they will do so in opposition to your basis change. This is called contravariance. Linear transformations are functions that transform vectors. Again, it's only when you represent them in a specific basis that they become tables of numbers which transform in a certain way. In the previous video, we saw that a matrix changes in two opposite directions at once. That's because it contains a contravariant vector part and a covariant dual vector part. We discovered that this is where the sandwich product comes from. As you can see, it's really easy to predict exactly how a tensor's components will change when we move to a new basis. I already showed you how to obtain the components of a tensor. You first pick a basis and write all of the individual pieces as rows or columns. And then you just tensor those together. To tensor one table of numbers with another, you just multiply each number on the left with the entire table on the right, and then you collect the resulting tables in a new nested table. For tensors with more parts, you just get tables that are nested more deeply. The numbers obviously depend on your choice of basis, but they do so in a totally predictable way, thanks to the internal parts. When you move to a new basis, each vector part will be transformed with the B matrix, and each dual vector part with the F matrix. So we get a combination of P covariant and Q contravariant transformations. In the previous video, I showed you how this works for a matrix, where P and Q are both 1, which gives us the familiar sandwich product. We need an answer to one more hot question. How exactly does the temperature in my kitchen depend on our choice of basis? Remember that the temperature was the result of feeding a position vector as input into a one-form with vertical contour lines. This perspective treats the one-form as a function, and the position as its input. If you want to express this more symmetrically, you would say that the temperature is the inner product between a dual vector and our position vector. The reason I bring this up is to stress that this is not a tensor product, it's an inner product. Instead of gluing the two partners side by side, it throws them into each other's arms. The result is not a bigger tensor, but a real number, the temperature. I find that it helps to imagine the tensor product as producing bigger things, and the inner product as producing smaller things. Mathematicians call it a contraction for this reason. We typically write the inner product, the contraction, using a row and a column. For what I want to show you here, the numbers inside don't matter, only the shapes of the tables do. The contraction is a product between the temperature one-form, which is a row, and the position vector, which is a column. Now we move to a new basis. The vector is contravariant, so it transforms using the B matrix, backwards, in the opposite direction as the basis. The dual vector, however, is covariant, so it transforms in the same direction as the basis, using the F matrix. B and F are each other's inverses, so they cancel out, and we get exactly the same expression as before the basis change. This leads us to the inevitable conclusion that the temperature value doesn't care at all about your choice of basis. The co- and contravariants of our two friends conspire to cancel everything out very precisely. And that is a neat little trick that allows us to create invariant stuff from equal measures of covariant and contravariant stuff. Great! We now know how each tensor transforms under a basis change, and we know how to create things that are invariant. Second goal, check. I want to end by going over some of the notation and jargon that you will encounter when studying tensors. But allow me to first ask you to like this video and to subscribe to the channel if you haven't already done so. And remember that you get early access to all videos on Patreon, where you can also watch exclusive content that will never make it to YouTube. Our patrons can currently watch exclusive videos about finite Fourier analysis, contravariants in type theory, and more. Just set up an account using the link below the video. Thank you so much. And now, the notation. Tensor algebra is a big topic with many new concepts. The sad thing is that this beautiful but difficult subject is made even more difficult by the abundance of different notations and terminology. So let me list a few potential confusions that you have to pay attention to. To make a clear distinction between the different kinds of parts of a tensor, mathematicians typically use upper and lower indices. I haven't followed that convention in the videos because it would have been way too confusing. But you will have to get used to the notation if you want to study more deeply. This expression represents a vector. In 3D, the index I runs from 1 to 3. So this expression stands for a collection of 3 numbers, the 3 coordinates of the vector. Always be aware that even though this notation is very compact, it can stand for a large number of real values. The index I is written at the top, which indicates that the coordinates of a vector are contravariant. Contravariant indices look like exponents, but they aren't. Confusing, right? This second expression represents a matrix. A matrix is a 1, 1 tensor, where the lower letter is for the covariant index and the upper for the contravariant one. And this would be a bilinear form, with 2 covariant one forms inside. Again, in 3D, each index runs from 1 to 3. Let's do a slightly more complicated example. Our notation allows us to write a matrix vector product as a sum like this. The index I runs horizontally through each row of the matrix, and at the same time it also runs across the input vector, which is a column. The row and the column have opposite variances, and that's what allows you to contract them. You could also have noticed the opposite variances by the way the indices are placed in the formula. Every time you see the same index occur in a lower and in an upper position, you know that you can do a contraction. In the final result, the index I is gone, because we have looped over it, we have contracted it away. The result is a new vector, whose coordinates are contravariant because their index j sits at the top. When you spell everything out explicitly, the single equation actually becomes 3 different equations, one for each of the possible values of the free index j. I know this is a lot to take in. I'm just giving some hints for those of you who want to go further. Here's the expression for the product between 2 matrices. Always pay attention to the total number of indices, and then look for letters that appear twice. The letter k appears both as an upper and a lower index, so once again, we know that we have a contraction going on between a vector and a dual vector. They will annihilate into a real number. The end result of this expression still has an upper index I left over and a lower index j, so it must be a 1, 1 tensor. And that's exactly what we expect. The product of 2 matrices is indeed a new matrix. If you wanted to spell this one out, you would get 9 different equations, one for each of the elements in the resulting matrix. Here's an expression that you may be familiar with, the Kronecker delta. It's a 1, 1 tensor. In other words, it's a matrix. When I and j are identical, the value of the matrix element is 1. All other elements are 0. Which matrix does this represent? That's quite a surprise, isn't it? Now it gets even more confusing. The sum symbols are often omitted, because you always know which indices are being summed over. Just look for repeated letters. This is called Einstein notation, and it makes things much more difficult for newcomers. I mean, this is what the matrix product looks like now. Would you have guessed? Then there are the many different names that mean the same thing. The words one form, dual vector, covector, linear form, and linear functional all mean the same thing. To add to the confusion, physicists often say one form when they really mean a one-form field. And similarly, they use the term tensor for a tensor field. That's not just a single tensor, but an entire landscape of tensors, one at each point of space. We talked about this in the video about gravity and potential energy. Finally, the tensor product is also sometimes called the outer product, or the direct product. Okay, that's enough notation and confusion for one day. Let's end with a quick recap. Honestly, after producing the previous video about matrices, I wasn't sure whether it would be useful to dedicate another video to more general tensors. But I have to say I'm glad I did it, because many interesting ideas, concepts, and tricks came out of it. We learned that tensors are multilinear functions, but that they can also be single input functions. And they can also be seen as objects that we can manipulate. They contain simpler objects that transform in very specific ways under a basis change. In a particular basis, tensors are nested tables full of numbers. And so we got to float back and forth between multiple perspectives. Objects versus operations, multi-input versus single input, covariant and contravariant and invariant. That's the main goal of the All Angles channel, to unlock all of these different perspectives and to show the deep connections between them. I want to personally thank you all so much for being part of the journey.